Uh, okay, so at the end of the lecture tomorrow, I talked about something about the gauge transformation for general metric, which is conformal to Minkowski space by the conformal factor of the scale factor squared. So, some people has complained that they didn't know what I am doing here. So the key point is that I would like to find some gauge invariant quantity that is very important in the calculation of the scalar provisions. So in here, you see many different quantities here, especially this phi, this b, this e, and this psi. So 4 of them are of the scalar type, but 2 of them are just gauge redundant, so we can gauge them away, and 2 of them are kind of physical quantity. For instance, in the Newtonian gauge, we can choose b equals to 0, e equals to 0, and preserve only phi and psi. So these 2 things are connected to the anisotropic part of the energy momentum tensor. So if that anisotropic stress is 0, then we have only 1 scalar degree of freedom. That is what we want. We want to find some physical quantity that is convenient for studying the evolution of the scalar provisions. So once we solve the equation of motion for either phi or psi, or some combination of this with some energy density perturbation or something else, I will define such kind of quantity later, we can solve all of the other quantities. That's the key point for the scalar type perturbation. So to the linear level, we do not have to mix the different modes. So if we do the Fourier transformation, so every mode with different wave number is independent to each other. So we have to solve this equation of motion for mode by mode, and then we just look at them linearly. But if we go to next to leading order, say for instance, third order in the Lagrangian, then there might be some mixing. Especially this will be the case for the scalar-induced Gaussian wave, when the tensor perturbation is sourced by a quadratic order of the scalar provisions. So say something like this. So in this case, we need some convolution of these 2. So the different modes are just mixed together. But now, in the linear order, we do not have such a phenomenon. And there is a so-called decomposition theorem, which means that the equation of motion for different types of perturbations, like in the scalar, in this vector, and tensor, they just evolve also independently. So if we want to solve the equation of motion for scalar perturbation, we can just neglect all of the quantities about the scale, vector and tensor type perturbation, and so for the vector and tensors. This is extremely useful, as we have already seen, for the tensor perturbation, this Hij. So in the first lecture, I have already solved the equation of motion. I just give the equation of motion without any of the derivations, that it is something like this. Some source term, let's see. So this is something we can derive from the cosmological perturbation theory. And also we have the similar equation for the scalar perturbations. This is what I would like to do in this section. So let's continue. So we already have this kind of a gauge transformation for all of these quantities. So this is a 1, 2, 3, 4 degree of freedom for the scalar type. And we also have some kind of a transverse vector of this This is there are 2 degrees of freedom here, 2 of degree of freedom here in the Fi, and also we have 2 degrees of freedom in the tensor modes. So which means that in total we have 10 degrees of freedom, which is exactly the case in the 4 times 4 metric, which is symmetric. So the next thing we would like to do is by using of this, we can derive a similar transformation for the matter content, which is the prediction of the energy momentum tensor. This is defined in this way. So I saw some kind of delay in the writing. Just wait. Okay, so the fall velocity is I define as UMI x mu over d tau. This is the prober time with the coordinate. So into the leading order, yeah, that's pretty much expected. Please be careful that this is a little bit from the result of a flat spaceline or a Minkowski spaceline. Great. So have you heard of this previous lecture to here? I mean, from the beginning of
No, only to, you said in the leading order, you write this like this, but we didn't see the expressions.
Oh, okay. So to okay, to leading order we have this, and you can easily get it just from this definition, because it's on geodesic, and every proper time. Let's just say so the proper time d tau squared is minus ds squared. So it's just a eta d eta squared. So you immediately have d tau is a d eta. So this u0 is the eta divided by a d eta, so it's 1 over a. So then you have this formula. This is just to the leading order. If you want to go to the next to leading order, you have to be careful because now this d tau squared has changed because of the perturbed metric. It's 1 plus 2 phi. So d tau is a 1 plus 2 phi, 1/2 of the eta is approximately 1 plus phi in total. So then you have this, or approximate delta u0 is minus phi over a, and ui is just dxi over d tau. This is very easy. You don't have to take into account the provision here, because this dxi over at the eta is already a small number. It's supposed to be the peculiar velocity. And you have some similar quantities with one index down. So this VI is just VI because we use delta Ig or G, yeah, just delta Ig to raise one over. So it is convenient in this case to write down the peculiar velocity into a transverse and a longitudinal part. And this VI is some derivative and some transverse part. This is the, let me just make it clear. This is the symbol of the perpendicular. And this V is called velocity potential. Which will be very important in defining gauge invariant variables. And then we can write the provision to the energy momentum test. For perfect fluid. Otherwise, we might have some anisotropic stress in the special direction. Okay, in this case, at least we have to consider, as before, the transformation laws for all of these quantities, especially the energy density and the provision of the velocities.
Hi, can I ask a question?
Yeah, please.
Hello. Yeah, so can you, I just got confused with the notation. Could you go up, please?
Mm-hmm.
So you've written U subscript I equal to A U superscript I, and then you've written UI is U subscript I equals to U superscript I, delta ij to raise and lower. So is that, am I reading it correctly? Is this U or?
Yeah, this is U. Sorry. This is U. Yes.
Yeah.
And
No, on the line
is
below. The line below that.
below that.
Yeah. So yeah. So that I understand. There's U subscript 0. I understand. How did you get the next two expressions? Because they sort of, because in one case you've written U subscript I equal to A U superscript I, and then you've written U subscript I equals.
I'm okay. I'm very sorry for the confusion. Yes, yes.
Yeah.
That's because this U is supposed to be a 4 vector, and V is only a 3 vector. That's the key point.
Okay.
So
the
yeah. So U
right hand side has
is,
a V.
yeah. Okay. There is a G mu here. Yes, E squared. So it's Gij and you know that you have a squared of delta Ij Uj. So that's the reason. So you have A of V I here.
Okay, thank you. It just was a notational problem.
Yeah, yeah, it's just yeah. Maybe you should put a 3 in here. So the better way is to do it like this. But sometimes it's just neglected. Just keep in mind this way is a 3-dimensional thing. Anyway, so we need gauge transformation for, let's say, TMU stuff. In this case, for instance, we need the transformation law for the perturbation of a scalar. Let's see. So in general, if there is a scalar of Q, which depends on the coordinate of X, it can be expanded in a way that it is Q0, let's see, Q bar or something, plus delta Q. And then delta Q, this is a background level. And this is the perturbation of a scalar. Then under this gauge transformation of X goes to X tiered, it's X plus C alpha, this is what we said. We have delta Q goes to delta Q tiered, delta Q minus Q. Let me just use this one. Q gamma C gamma. Yeah. This is something I would like you to calculate by yourself. This is 4.3. It is quite easy if you are familiar with the Lie derivative, but if not, you can just expand it and get whatever you want. For instance, for the energy density, we have delta rho goes to delta rho tiered, which is delta rho minus rho prime. And this sometimes is written in the terms of delta t. But please remember that this doesn't mean some time shift, but it's gauge transformation or a kind of a redefinition of time. This will be useful later sometimes. For instance, this c can be the displacement of some different gauge. Like for instance, define this delta t to be time shift between uniform density gauge, this means delta rho is 0, and the uniform curvature gauge. This means psi is 0, because if you remember correctly, that in here, let me just make it, this psi, oh, sorry. This psi is the term that appears in this manner in the special part. So this is called the curvature provision. In any gauge, because we don't fix the gauge yet. So this psi is the curvature provision in any gauge. So in a specially flat gauge, this means that in the special part there is no curvature, so psi is 0. So you can always find a time redefinition where the coordinate time, okay, the conformal time is delta eta, the cosmic time is delta t, that you can transfer the gauge from the uniform density to uniform curvature. So in this case, if we look at this formula, we can find that on the left-hand side, because it's the uniform density gauge, we have this, right? So it is 0. And on the right-hand side, okay, let me just write more clear. So it's delta rho prime is delta rho delta t. So this is in the uniform density gauge. This is in the flat gauge. And this left-hand side is 0, right-hand side is delta rho in the flat gauge minus rho dots of delta t from uniform density to flat. So then it's very easy to define the so-called curvature provision in this way. Because in curvature provision, you can take the coordinates backwards. The curvature provision in a flat gauge is defined as the symbol of zeta. I will come back to this later. So this is defined as psi in the uniform density gauge. So then you can get this back by the transformation of this, right? You know that the transformation backwards is from here. Right? Now you know that delta t, so let me just write a few more words. So so you know this is just psi minus h delta t, right? If you want to transfer it back. So we already know that delta t here is delta rho or rho dot. This special, let me just write it, capital T, delta t. Then you have this. So this, remember, this is in the especially flat gauge. In this manner, you can move it back. Then you have the famous formula that this kind of thing is psi minus delta rho over rho dot h. So this is the definition of the curvature provision in uniform density gauge in the sense of the flat gauge. Of course, this is 0 in a flat gauge. Right. I will come back to this later, but this is just some first sight of how to do the gauge transformations for the important quantities. There is another transformation law for the vector, especially the field velocity. So you can also prove this. And this is useful, I think, in some problems, but I'm not quite sure if I just write it down anywhere. Anyway, so as we have shown that this delta phi, delta u naught is not independent. But delta ui is, and has 3 degrees of freedom. Let me just write it here. This is because we said this is a minus a phi. We have derived this sometime earlier. Okay, now we go to the second part, which is seeking for gauge invariant quantities. For a scalar provision, of course. The basic method to do this is to go back to this transformation law, to all of this. And you can find some combinations of this as I have done in here. Like in this way, you find the transformation of the time or space between different gauges. And you then just try to combine all of these quantities in a way that doesn't depend on the gauge transformation. For instance, if you look at this and this is 1 and 2, you can immediately see that if I make 1 minus 2 prime, then you have B tiered minus E tiered prime is B minus E prime plus C0, and the C prime is just eliminated. And in this way, you can write C0 in a way that it depends on B and E only. So this is the way that you can find for the gauge transformation written in the form of this two of the metric provisions. Then, given that, let me just write it here again. And you can do it in the way that many of the other quantities many of the other transformations rely on this C0. Like, for instance, this one, we write 3 here. So just reread this. So for 3, you have this criteria is phi minus 1 or A of A, and you substitute this result. Right? And then you can always move this part, which belongs to the tiered coordinate, to the right, to the left. Right? Then you find that this combination does not depend on the gauge transformation, because the gauge transformation, the 4 vector for the gauge transformation, infinitesimal gauge transformation vector, doesn't appear in this combination. So we can define a new variable, which we call this capital phi, to be this, and this thing is gauge invariant. And this is the physical meaning is the Newton potential in some specific gauge where B and E are 0. This is called the conformal Newton gauge. And also similarly, if you look at this 4, you have a similar formula. Let me just write it in another color. So psi tiered minus equals to psi minus a prime over a, or a, b prime minus a prime tiered. Oh, sorry, there is a prime I have missed. Yes. And similarly, you have defined as a capital psi. This is called the curvature perturbation in conformal Newton gauge. Wait, there is something wrong. Let me check my note. Not. Let's see this change. There's an A factor missing. Oh, sorry.
There are no A's in the Xylophone.
Yeah, there is a no inside the parenthesis. I'm sorry. Yeah, no, it's fine. Yeah. So we have defined the Newton potential and the curvature perturbation in the gauge of B equals to E equals to 0, which is called the conformal Newton gauge. This is very useful. We focus on this sometime later. The key point is that if we take this gauge, then everything can be written in a compact form. For instance, the metric sorry, there's an A squared. This is the, surely this is a scalar part. The scalar provision, scalar part of the perturbed metric can be easily written in this way. That's the advantage of the Newtonian gauge. And if there is no anisotropic stress, which I will talk about later, that we will have an equation of motion that the sum of this is proportional to, let's see, some anisotropic stress tensor. So if this is 0, as is the case for many of the perfect fluid case, then you don't have 2 of this degree of freedom. You have just 1 of them. You can use either phi or psi as your variable, and that is the only variable, dynamical variable in the early universe. And you can put it first, find the equation of motion. So you have the S squared is something something that is proportional to this, for instance, and you get the perturbed Einstein equation to find the equation of motion of phi. And you can evolve that until today and connect that to the CMB anisotropy, the large scale structure, and so on and so forth. Delta T over T, delta rho over rho, and something. That's the basic idea of the primordial cosmology. But besides that, we have some kind of other kind of such gauge invariant quantities. And some of them are quite important. As you can see from here, that a combination of any of 2 or more gauge invariant quantities are also gauge invariant. But just keep in mind that the degree of freedom of this scalar type perturbation is only 2. And if you are in a diagonal part of the energy moment tensor, then you only have 1 of the degree of freedom. So you can use some other different types of the invariant quantities, but you only have 1 degree of freedom, which means that they must be combined to each other to give you the equation of state. So everything will come in. For instance, you can define a gauge invariant energy density. And by this, you can have the so-called uniform density gauge. This can be done by looking at the transformation of that rho here. This equation I have a mark. Let me just put a number. That's the 5. Just up to here. Okay. So from this, you see that you can express this C0 into the difference of the energy densities perturbation. Be careful that this is the background level result. So I should write something like this, but I just forget it. So in this case, you can substitute this into this equation, let's say 6. So they are the same thing, which give you that this can be defined as a gauge invariant version of the density energy density perturbation. And the physical meaning is that it is energy density in conformal Newtonian gauge. This means that even if we set a coordinate that the energy density perturbation is 0, we still have this quantity. This is the what we have for the gauge invariant quantities. That the value of such quantities doesn't depend on which coordinate you choose. So in this kind of quantity, another important one which we will frequently use is the field perturbation. So scalar field, For instance, the inflaton, which drives the inflation, is also a scalar. That's the same as the energy density, right? So it must have the same quantity like this one. So I just write it in here. Sometimes this is written as Q. It is called the field perturbation, the gauge invariant field perturbation, and sometimes also called the Mukhanov-Sasaki variable. You can find the equation of state purely written in terms of Q. And the physical meaning of Q is that it is the field perturbation, that's the inflaton field, in Newton gauge also. So as you can see, you can have equation of motion of phi, and you can also have equation of motion of Q. They are basically the same thing. Even though in the same gauge, they are the same thing. So they must be connected. And the way to connect them, you can choose another gauge that can combine all of these qualities together. So this is the case that we define the so-called uniform density gauge, as I just introduced before. For this manner, let's go to here. This is the first equation we would like to know. And we have the equation for psi here. From this, we know C0 is psi tiered minus psi divided by Hubble, right? So then we combine with this one. We have let me make sure that the signature is right. So the psi tiered minus psi, but delta rho minus delta rho tiered. Then you have psi tiered divided by psi plus I think something is wrong. The signature, the sign is not right. Let me check. I don't know. Prime. 7-1. Oh, sorry.
Psi minus psi tilde.
Yeah, psi minus psi tilde. I'm so stupid. Thank you. Yep. And then we have so this is a kind of a gauge invariant variable. We define it as zeta. The meaning of zeta, the physical meaning of zeta is that it is the curvature perturbation in uniform density gauge. Because in uniform density gauge, this delta rho term is 0, and you only have psi. And we know that psi is the curvature perturbation in any gauge. That is one of the problem you have to solve. Some people will just call zeta curvature perturbation for short. And they refer it to the curvature perturbation in the uniform density gauge, but just discard the condition of the gauge condition. In principle, strictly speaking, that is wrong, but it is in some sense conventional for some authors. You can use this term, but when you write it, please be aware that it is only the perturbation of 3 curvature only in the uniform density gauge. Otherwise, it is the combination of these two. It is combination of the curvature perturbation, which means that the perturbation in the curvature term, the Ricci curvature in the 3-dimensional metric, and another term that comes from the field energy density perturbation of the source term, the energy momentum term. I think this is a problem. 4.4, but I haven't finished the problem sheet yet. I will do it later, just right after the this session. Okay. This is to let me just write it here. Please wait. Show this. Yeah, it's in here. So the problem. This is to help you to understand the physical meaning of the curvature perturbation. So in the perturbed metric, derive the 3-dimensional Ricci curvature this K is the wave number, comoving wave number. Usually, there is another frequently used quantity that is the curvature perturbation in the comoving gauge, which means that the gauge means that the matter co-moves with the space-time. And that is the velocity potential equals to 0. So I will talk about this in here. This is the 4.2, okay. So as I have said, that we want to transfer the field perturbation in this way. and you substitute everything in, and you have right. So this is just because this one is just a U naught, X naught, prime. And you substitute the result that cosine naught is B tiered over E tiered minus B minus E. And U naught is so by the same trick, you move all of the tiered coordinates to the left. Then you immediately see that this is also a gauge invariant quantity, which you can define as delta U naught bar. But this is nothing but a combination of two, one already known quantity, if you remember it correctly. Because forget about this, because this delta U naught is just minus A phi. So this quantity is just minus A phi plus A B minus A prime. And this is what we already know, that the capital phi, the Newton potential in the Newtonian gauge. So this one is just minus A capital phi, as we have said, that it is not independent degree of freedom, but it depends solely on the gene on the Newton potential. Similarly, we can do the same thing for the special part of the velocity provision. So this is a kind of a quantity we can define as the gauge invariant velocity. And the key point here is what we have discussed before, that we can expand this quantity. Right? And as we said, that this part is the connected to the vector part, so you don't have to care about it. And now we have delta U I delta U A B. So the scalar part is just this. Right? And therefore, according to what we have shown in the previous session, that we have this. You can do it in the same way for this delta U. Let me check the numbers. The signature is. Oh, sorry. Let's go from here. Yeah, it's fine. So you can put them together with the cosine knot. Let me make sure that this is correct. Yeah. So this is a gauge invariant quantity. And this is a very important one. In the cosmic time, it is just ordinary Hubble. This is defined as the curly arc, whose physical meaning is that it is the curvature perturbation in comoving gauge. Comoving means the velocity potential is 0. So then you have this is 0. You only have this psi. So this equals to psi in the sense that it is the curvature perturbation in the gauge that the velocity potential is 0, which is the so-called comoving gauge. Sometimes also call this quantity as comoving curvature perturbation for short. That's also okay. But you will see that this quantity is a little bit similar to the zeta here, and somebody will use it without any further notice as the same thing. But actually, they are only the same thing on super horizon scales, as I will show you later in the dynamics. But they are not the same in inside the horizon. The difference between them is proportional to the wave number squared. So it is huge when you go inside the horizon. because basically they are two different gauges. Delta U equals to 0 is in the case of the inflation, it is also always in principle equivalent to delta phi equals to 0. But delta rho is not only does not only depend on delta phi, but also depend on the metric perturbations. So that's the key point. We will show that later. So there will be a problem anyway. So I think I leave it yesterday, but I think maybe it's difficult to be solved yesterday. Okay, I just write it here. So the problem is to prove that zeta is a constant on superhorizon scales that is the wave number is much smaller than the comoving Hubble factor, comoving Hubble rate. Yeah. And this can be done in the following way. First, if we take the conformal Newton gauge, everything is very simple. So you have dx squared, a squared eta. Let me just write it in the gauge invariant way. And you can show the Christopher symbols. I write it in the problem. You can check it by yourself. And then you can calculate the energy momentum conservation. Of course, to the perturbed level. This will give you a perturbation equation that's the rho prime plus 3h, delta rho plus delta p plus 3 rho naught, p naught, psi prime minus nabla squared v equals to 0. This v is the again the velocity potential. This is the second step. And the third step is to prove that zeta is a constant when this term can be neglected. Basically, this is just based on this equation, but this depends on some kind of a argument, some thinking about how to transform your gauge from the one we are working on to the gauge which zeta is defined, and that is the uniform density gauge. So I think this is a very good practice for what you have learned from here. Okay. So then I will go to the dynamical part. The perturbed Einstein equation. I think I only have time to write it down, but I really don't want to derive it in here. Okay. Basically, these right-hand side are defined in a gauge invariant manner. Let me just write it in this way. So this is something that you can prove by yourself, that you can always define this gauge invariant a metric perturbation by the discussion we have had before in this way. So delta t let me just leave it in the for the problems. Okay. Then we have to go to the easiest way to understand this formula is that because everything is written in the Newtonian gauge, we just take everything to be, we can do it like this. We fix the gauge to be the Newton gauge, and everything can be written in this coordinate. And this may help you to understand this equation. Okay. Anyway, so we have the following metric, the perturbation for the energy momentum tensor. This is what we have derived before, but I prefer to just write it here. And then you substitute this part into the Einstein equation. And finally, you have something like this. The last part is the so-called anisotropic stress tensor. And usually, it is 0 in the case when we do not have such terms in the energy momentum tensor. So it can be greatly simplified to set this to be 0 in at least when we calculate the scalar provisions. And it will be important when we have the neutrinos. Neutrino free streaming will contribute to that. That is the most contribution to this in the late universe. But currently, let's just set this to be 0. And we have that the psi is -5. This is because there are some constant for these integrals. But if we just push the border to infinity, then the constant must be 0. So we have this, and then substitute back into these equations. we can greatly simplify this equation. And the most important one is we use this one. So firstly, we notice that this is important when we want to connect the velocity potential to the phi and psi. So, but because it introduces a new degree of freedom, but we do not need it here. So this is to fix V. And we have this one and this one. To know that, we have to know the equation of state for this perfectly fluid thing. The first thing we would like to do is to make, let me just write it 1 and 2. So 2 minus 1 times the CS squared. I suppose CS squared is the sound speed. It's partial P or partial. Then finally, we have so we see that this is an equation of motion of phi only. So this is called the master equation in the of the metric provision in the early universe, written in the terms of the Newton potential of the Newton gauge. So the source term, basically it is an equation of the wave equation, like with a decaying amplitude, but there is a source term which only depends on the non-adiabatic matter. So for adiabatic matter, when you have delta P is just CS squared delta rho. So this term is 0. We do not have any source term for non-adiabatic, for adiabatic matter. It is, for instance, if we are working in one single component of perfect fluid, then we do not have this term. Everything is very much easier to be solved. I think I will just stop here. And for solving this equation and the discussions for the solutions in the during inflation and during the radiation and matter-dominated universe, and its connection to the quantization deep inside the horizon, and something. And I think I will talk about the solution of this equation and the initial conditions tomorrow, together with the equation of motion for the tensor modes, and the initial condition and the primordial, how to solve the primordial tensor fluctuations. That's the lecture I will give tomorrow. And on Friday, I will tell you how to connect this scalar provision to source the gravitational waves in a manner that we go beyond the linear level of the provision theory, but go to the next leading order where the tensor provision and the scalar provision are coupled. And in that manner, the projected scalar provision becomes a source term of the tensor provision in a manner that you have, for instance, you know that the equation of motion is like this.
Hello.
It's fine. I don't think it's for me. There is a telephone ring. Sorry.
Sir, I think phone is ringing.
Yeah, but I don't think I have to answer it. It's fine. That's not my phone. So, it's so you have a source term, which is something like you know that we have already know that you have this projector, right? And you have partial L of the Newton potential and partial M of the Newton potential and something similar things like that. This is what we would like to learn from the so-called induced quantum wave of the second order. And to do that, we must know the behavior of the Newton potential in the thermal universe. Its generation during inflation, its evolution in the radiation-dominated universe, and which is governed by this master equation, which I will discuss tomorrow. I think I just stop here and take your questions.
Thank you, Shi. We have time for questions. So you can either unmute yourself and ask or type on the chat box. I would appreciate if people don't leave yet. After the Q&A session, we would like to have a group photo taken.
Oh. So everybody is going to show their video.
Sorry?
Yeah, are we going to take a photo here now, or?
Yeah. After the question.
After the question.
Yeah.
Is there any questions? I think these are kind of a little bit tedious for the people who are not familiar with the cosmological perturbation theory. But I think I tried my best to make things as easy as accessible as possible.
Yeah, totally agree. Hopefully, this tutorial sessions would give them like a really hands-on. One really has to work out these things to understand. So hopefully, the tutorial sessions would fill the gap. So Kaushik Paul has a question.
Please.
Yeah. So I couldn't understand the last step where you have put the value of CS square in and subtracted equation 1 from 2. So
yeah, that's just to make the equation sourceless in the case of the perfect fluid. So we observe that this equation 1 and 2. Sorry, let me just share the screen. So our main task is to solve these equations. Let's see. So we want to solve these equations 1, 2, 3. Let's see, 3. So we notice that there are on the left-hand side there are two kind of variables, phi and psi. Okay, there is a 4. So by 4, phi equals to minus pi, then we have only one variable. So in this case, the only thing we have to care about is the source term on the right-hand side. So this will introduce a new source term, the velocity potential. So we just forget it. And for these two terms, we have a left-hand side equation of motion here, but these two things to our knowledge are kind of connected. So in a way that it is 0 in this combination for the perfect fluid. So that's the reason why I do that. I subtract this delta rho delta p minus CS squared delta rho to make it just 0 for perfect fluid, because that's the most commonly used case for the cosmological perturbation theory. Like for instance, in the radiation-dominated universe, the matter content is just a fluid of relativistic particles. Then you can always make this equals to 0. So your equation becomes a sourceless equation, and this is much easier for you to solve it.
Thank you, Professor.
Are there any last questions? Okay, if not, we'll go for the group photo.